Lecture 34 is our final lecture on dielectric properties of materials. In this lecture, we further talk about dielectrical loss, and then we talk about different breakdown mechanisms and the dielectric strength of materials. And finally, we talk about three different dielectric responses: piezoelectricity, ferroelectricity, and pyroelectricity. So the first student learning outcome is that you should be able to name multiple different dielectric breakdown mechanisms, and specifically, you should be able to describe what happens on the avalanche breakdown. So avalanche breakdown is also called intrinsic or electronic breakdown. It happens in all materials, but under very high electric field. When an electron somehow or a hole somehow exists in the material, if the electric field is really, really high, then they could gain sufficient kinetic energy before they scatter with additional electron in the valence band. That scattering may induce that electron to transition from the valence band to the conduction band. So basically, you have one electron you start with, or hole start with, and then you end up with three charges. So this multiplication process can go on forever, and then that's why we so-called avalanche situation happens. So obviously, the requirement is that the electron or the hole, the original electron or hole, should gain sufficient energy. And so if you do a simple estimation that requires electric field on the order of megavolt per centimeter to induce such electronic breakdown process. Once you remove the electric field, then the multiplication process will go away. So this is sort of a reversible process. There's no permanent damage to the lattice. No atoms are moving. Only the electrons are jumping up and down from the conduction in between the band gaps. There are other breakdown processes that involve permanent damages to the material, such as thermal breakdown, electromechanical breakdown, internal discharge, or external discharge mechanisms. And obviously, all these mechanisms may depend on many situations, how you use this material, the geometry, the humidity, and many, many factors about the conditions of using these materials. The second student learning outcome is related to the three different dielectric responses: piezoelectricity, ferroelectricity, and pyroelectricity. So you should know what these effects are, and then how you define the relevant figures of merits to characterize the strength or magnitudes of those behavior. So for piezoelectricity, it's a process when a mechanical stress induces polarization, or an electric field induces polarization, and that polarization results in mechanical strain in these materials. There are many examples. Quartz, barium titanate, these are the materials that exhibit piezoelectricity. To characterize the strength of piezoelectricity, people define the so-called piezoelectric coefficient. Basically, here the P is induced polarization, and T is the mechanical stress, and then D is the piezoelectric coefficient. And in general, that D could be a tensor because the polarization may not occur in the same direction as the mechanical stress. For example, in the case of hexagonal unit cells, if you apply the mechanical stress in the vertical direction, that will induce a polarization in the same direction. But if you apply the stress in the horizontal direction, it will still result in the polarization in the vertical direction. So that piezoelectric coefficient typically is a tensor. There's also the ferroelectricity. In some systems, when there are permanent dipole moment existing in unit cells, these materials may have a finite polarization vector even in the absence of applied electric field. Okay, and this is existing in material like in barium titanate at a temperature above a certain Curie temperature. It's non-ferroelectric because the positive charge center and the negative charge centers are exactly at the same place in the unit cell. But when you cool it down to temperature below the Curie temperature, then the titanium ion actually will be displaced from the center of the cubic unit cell. That changes the symmetry to tetragonal, and then also creates a permanent dipole moment within that unit cell. And so the alignment of that these dipoles within each unit cell could give you a finite polarization in this material, even in the absence of electric field. And obviously, in that case, all these ferroelectric crystals will be piezoelectric as well, but the reverse is not necessarily true. For pyroelectricity, basically the polarization could be caused by a difference in temperature across the two faces. When the temperature changes, the lattice constant changes, and so for for materials like piezoelectric materials that will generate different displacement of ions and dipole moments within each unit cell, and that will induce a polarization across the two faces of the material. So to define the pyroelectric coefficient, this is a way of defining that the delta P over delta T. The change, how much polarization is changed when for a certain difference of temperature across the two faces. For ferroelectricity, specifically, you also want to know a few things: saturation polarization, remnant polarization, coercive field, and describe the hysteresis loop when you look at the polarization as a function of electric field. So in piezoelectric material, the actual polarization existing in these materials does depend on the history of treatment. Okay, in the absence of electric field, when you cool it down from above the room Curie temperature to below Curie temperature, then no polarization will occur. And this is because in the system, actually, you have many different domains, and the polarization within each domain may be aligned, but then in between domains, the alignment may be random. So overall, your system may appear with zero spontaneous polarization. So you could induce a finite polarization by applying the process called polling. Basically, you can apply the E field during the cooling process to align those dipole moments in a particular direction. Or you can apply this, you can look at the hysteresis loop of polarization as a function of electric field. If you start with a material that's unpolarized, you can increase the polarization by applying an E field. And this is really because that you're partially aligning those dipole moments in the direction of the E field. And so in that case, the polarization, you can look at the change in polarization as a function of change in E field. So with that, you can define a dielectric constant, which actually is very high for ferroelectric materials, could be on the order of thousands in certain directions. But once you apply a really high electric field and then all the dipole moments are aligned, that's when you get to a maximum polarization. This is so-called saturation polarization. If you slowly release the E field back to zero, then since the dipole moments are partially aligned, you will not be able to remove the polarization completely. That gives you a so-called remnant polarization right here. Okay, to completely remove the polarization, you have to apply the electric field in the opposite direction. That's a so-called coercive field. And then if you further increase the E field in the opposite direction, you can actually realign all these dipoles in that opposite direction. That gets you another saturated situation. So that's a saturated polarization as well, but obviously in the opposite direction. And then when you go back and reduce the E field and slowly getting back to the forward direction, then you will have, when your E field is zero, you still have some remnant polarization, and then you have to apply a coercive field in the original direction to completely remove the polarization. That's also the coercive field. And then that's why we have a hysteresis loop, and that means the polarization is not a single value function of the E field. It does depend on the history of operation or how much E field you have applied to this material. So that is the end of this review.